There is a structure in the observable universe so enormous that, according to the very laws of physics that govern how matter clumps and organizes across cosmic time, it should not exist. Not, it's surprising that it exists. Not, it's rare. According to the standard model of cosmology, the most rigorously tested framework humanity has ever built to describe the large-scale architecture of reality, a structure of this size and mass should be physically impossible. The universe has not had enough time, in its 13.8 billion years of existence, to grow something this large. And yet, there it is. The Hercules Corona Borealis Great Wall, a filament of galaxies, galaxy clusters, and the dark scaffolding of matter that binds them, stretching approximately 10 billion light-years across. 10 billion. To write that number is easy. To understand it demands something else entirely. A single light year, the distance light travels in 1 year, moving at approximately 300,000 kilometers per second, equals roughly 9.46 trillion kilometers. Multiply that by 10 billion, and you are looking at a number so far beyond the reach of human intuition that our ordinary tools of comprehension simply fail. So set aside the numbers for a moment and think about scale in a different way. The Milky Way galaxy, our home, the structure containing our sun, our solar system, every human being who has ever lived, every civilization ever recorded, measures approximately 100,000 light-years in diameter. The Andromeda galaxy, our nearest large galactic neighbor, sits about 2.5 million light-years away. The distance between the two of them, across the void of intergalactic space, is already incomprehensible by human standards. Now consider that the Hercules Corona Borealis Great Wall contains the equivalent of that entire gap, that 2.5 million light-year chasm, repeated 4,000 times end to end just to span its length. That is not a galaxy. That is not a cluster of galaxies. That is not even a supercluster. It is a structure so far above those categories that the scientific community had to reach for entirely new language to describe it. The word they settled on is Large Quasar Group, or LQG, a term that only hints at the reality. A gravitationally coherent web of active galactic nuclei embedded in filaments of dark matter, forming the largest known coherent feature in the observable universe. The Hercules Corona Borealis Great Wall was identified through the distribution of gamma-ray bursts, the most energetic explosions in the known universe, briefly outshining entire galaxies, visible across billions of light-years. When astronomers Istvan Horvath, Jan Hakala, and Zsolt Bagoli published their analysis in 2014, the astronomical community did not celebrate. It was troubled. Because this structure, if it is truly gravitationally coherent, violates what cosmologists call the cosmological principle, the foundational assumption, baked into every major model of the universe's large-scale structure, that matter is distributed uniformly when viewed at large enough scales. That the universe has no preferred directions, no edges, no seams, no structures that dominate the view from any one vantage point. Beyond a certain scale, roughly 1.2 billion light-years, according to theoretical predictions, the universe should look the same in every direction: smooth, homogeneous, isotropic. The Hercules Corona Borealis Great Wall is roughly 10 billion light-years across. That is not a minor deviation from the expected upper limit. It is an anomaly of a magnitude that forces a choice. Either our instruments and statistical methods are producing a phantom, a structure that only appears coherent because of how we are sampling the data, or the universe, at the largest scales we can currently observe, contains something that our best physics cannot explain. Neither answer is comfortable. To understand how we arrived at this question, you have to go back to the architecture of the cosmos itself, to the way the universe builds its largest structures from the ground up, one gravitational whisper at a time. In the immediate aftermath of the Big Bang, the universe was not a smooth, featureless plasma. It was almost smooth, almost featureless. Tiny quantum fluctuations, perturbations in energy density barely larger than the background, were stretched to macroscopic scales by the rapid expansion of the early universe in the period known as inflation. These fluctuations, imprinted across space like the faintest possible variations in texture, became the seeds of everything. As the universe cooled and matter decoupled from radiation roughly 380,000 years after the Big Bang, the moment captured forever in the cosmic microwave background, the oldest light we can detect, those tiny overdensities began to grow under their own gravity. Matter drifted, slowly at first, then faster, toward the regions where density was slightly higher. Over hundreds of millions of years, gas clouds collapsed into the first stars. Stars exploded and seeded the cosmos with heavier elements. Gravity pulled matter into halos of dark matter, and those halos merged into larger structures. Galaxies, groups of galaxies, clusters, superclusters. The resulting large-scale structure of the universe resembles, in its most faithful description, a cosmic web. Vast sheets and filaments of dark matter and luminous gas threaded through space, with galaxy clusters concentrated at the nodes where filaments intersect, and enormous voids, regions nearly empty of matter, occupying the spaces between. This web is not metaphorical. It has been mapped, measured, and simulated with extraordinary precision by surveys like the Sloan Digital Sky Survey, which cataloged the positions of more than 3 million astronomical objects across roughly a third of the sky. Within this web, enormous structures have been cataloged. The Coma supercluster. The Shapley concentration, a massive overdensity of galaxy clusters visible in the direction of the constellation Centaurus, roughly 650 million light-years away, containing more than 8,000 individual galaxies. The Sloan Great Wall, identified in 2003 from Sloan survey data, stretching approximately 1.4 billion light-years, which was, at the time of its discovery, the largest known structure in the universe. Then came the Hercules Corona Borealis Great Wall. At 10 billion light-years, it does not merely break the previous record. It shatters the theoretical ceiling entirely. The Sloan Great Wall sits just above the cosmological principle's predicted upper limit, close enough that the community could treat it as a statistical edge case, a feature that sits at the boundary of what the standard model can accommodate. The Hercules Corona Borealis Great Wall is nearly 7 times larger. There is no comfortable place for it within the framework. It is worth pausing on what the cosmological principle actually means, and why it matters so much that it must not be broken. The principle is not an observation. It is an assumption, a foundational prior that the universe on the largest scales is homogeneous and isotropic, that no location in space is fundamentally different from any other, that no direction is privileged. This assumption is what makes modern cosmology mathematically tractable. It is what allows cosmologists to write a single equation, the Friedmann equation, derived from Einstein's general relativity, that describes the expansion of the entire universe without specifying a particular point in space. Remove the cosmological principle, and that equation no longer applies to the universe as a whole. The entire standard model of cosmology, including the lambda CDM model that currently best fits the observational data, rests on this assumption. A structure 10 billion light-years wide does not merely challenge that assumption. It pulls at the foundation of the entire edifice. And the most unsettling part? The Hercules Corona Borealis Great Wall is not alone in raising these questions. In 2021, a team of astronomers identified a ring-like arrangement of gamma-ray bursts, designated the Giant Arc, stretching roughly 3.3 billion light-years across the sky. In 2022, a structure called the Big Ring was identified, an enormous circular arrangement of galaxies approximately 1 billion light-years in diameter, located at roughly the same cosmic distance as the Giant Arc. These structures are not causally related. They are not physically connected. But their existence in the same region of the observable sky, at roughly the same redshift, compounds the anomaly rather than explaining it. The universe keeps producing features at scales where the cosmological principle says features should not exist. The question is no longer whether these structures challenge the model. They do. The question is what the challenge means, whether we are looking at observational artifacts, statistical flukes born from the way we sample an incomplete sky, or whether the universe genuinely contains large-scale geometry that no current physics can account for. That question drives everything that follows. On November 19, 2013, a paper submitted to the journal Monthly Notices of the Royal Astronomical Society quietly detonated inside the cosmological community. István Horváth, John Hakala, and Zsolt Bagoli, a team of American and Hungarian astronomers working with data from NASA's Swift gamma-ray burst mission, had been mapping the spatial distribution of gamma-ray bursts across the observable sky. What they found in the constellation region between Hercules and Corona Borealis was not a galaxy, not a cluster, not a supercluster. It was a statistically anomalous concentration of gamma-ray burst sources at similar redshifts, stretching across a portion of sky so enormous that, when translated into physical scale, the resulting structure measured somewhere between 10 and 15 billion light-years in its longest dimension. The reaction from the broader scientific community was not awe. It was skepticism. Careful, methodical, rigorous skepticism. The exact kind of response that makes science function. To understand why, you need to understand what a gamma-ray burst actually is, and why astronomers use them as cosmic distance markers in the first place. A gamma-ray burst is the most energetic electromagnetic event known to occur in the universe. They are produced in two primary ways. The core collapse of a massive star at the end of its life, a process that, in its final moments, produces a jet of gamma radiation so powerful it briefly outshines the combined light of every star in the Milky Way, not for millions of years but for seconds, and the merger of two neutron stars, the ultra-dense remnants of previously collapsed stellar cores. In either case, the resulting burst of gamma radiation travels outward at 300,000 kilometers per second, traversing billions of light-years of space before reaching our detectors. The Swift satellite, launched by NASA in November 2004, was specifically designed to catch these events, calculate their position on the sky within seconds of detection, and relay that position to ground-based telescopes for follow-up observation. Because gamma-ray bursts are so energetic, they can be detected across the full depth of the observable universe. That makes them uniquely valuable as probes of the large-scale structure of space. A galaxy emitting visible light becomes undetectable beyond a certain distance. A gamma-ray burst at its peak luminosity cuts through billions of light-years of intergalactic space and arrives at our instruments with enough energy to be precisely located and measured. Map enough of them, and their spatial distribution should trace the underlying distribution of matter across the cosmos. What Horváth's team found was that the gamma-ray bursts in the Hercules Corona Borealis region were not distributed randomly. They were clustered. Not in the way that random distributions occasionally produce apparent clustering through statistical chance, but in a way that, when subjected to standard tests for spatial randomness, returned a confidence level suggesting the clustering was real. A genuine overdensity of sources at a common cosmic distance. The problem, stated plainly, is time. The Hercules Corona Borealis Great Wall sits at a redshift of approximately 2, meaning we observe it as it existed roughly 10 billion years ago, when the universe was only about 3.8 billion years old. Redshift, to be precise, is the stretching of light's wavelength caused by the expansion of space itself. As the universe expands, the light traveling through it is stretched toward longer, redder wavelengths. The amount of that stretching, the redshift value, is a direct measure of how much the universe has expanded since the light was emitted, and therefore a precise proxy for cosmological distance and look-back time. A redshift of 2 means the light we are detecting left its source when the universe was roughly 27% of its current age. Now consider what the universe looked like at 3.8 billion years old. The cosmic web was younger, sparser, and operating under the relentless but slow process of gravitational assembly. Dark matter halos had been accumulating mass since the first 100 million years of cosmic history. The earliest galaxies had already formed. Observations by the James Webb Space Telescope, operating at infrared wavelengths to pierce the veil of cosmic redshift, have since confirmed galaxies existing within a few 100 million years of the Big Bang, earlier than many models predicted. But building a large-scale coherent structure requires something beyond individual galaxy formation. It requires the slow, hierarchical merging of smaller structures into larger ones, halos merging into groups, groups merging into clusters, clusters pulled together by the gravitational influence of large-scale dark matter, overdensities into superclusters and filaments. This process has a speed limit. Not in the sense that matter moves too fast, but in the sense that gravity, operating across billions of light years, cannot organize matter faster than the universe's own expansion allows. The rate at which large-scale structure grows is governed by the competition between gravitational attraction, which pulls matter together, and the expansion of space, which pulls everything apart. In the early universe, before the accelerated expansion driven by dark energy began to dominate, which happened roughly 5 billion years ago, gravity had the upper hand on small scales. But on scales of billions of light years, the sheer distances involved mean that gravitational influence propagates slowly and hierarchical assembly proceeds at a measured pace. Cosmological simulations, the most sophisticated of which, including the Millennium Simulation and the illustrious TNG project, run on some of the most powerful supercomputers ever built, model this assembly process with extraordinary precision. They begin with the initial conditions derived from the cosmic microwave background, seed the simulation with the observed density fluctuations, apply the known laws of gravity, fluid dynamics, and dark energy, and let 13.8 billion years of cosmic evolution unfold in accelerated time. The resulting simulated universes reproduce the observed large-scale structure with remarkable fidelity. The filaments, voids, cluster nodes, and galaxy distributions match observations across a wide range of scales. These simulations consistently produce a theoretical upper limit for coherent large-scale structures. The number is not arbitrary. It emerges directly from the physics of gravitational growth rates in the age of the universe. Structures larger than approximately 1.2 billion light-years, roughly 120 megaparsecs in the units cosmologists typically use, should not exist as gravitationally coherent entities. The universe simply has not had enough time to assemble them. The Sloan Great Wall, discovered in 2003 using redshift survey data from the Sloan Digital Sky Survey and stretching approximately 1.4 billion light-years, already pressed against that boundary. At the time of its discovery, its size provoked genuine discussion about the cosmological principle's validity. Subsequent statistical analyses suggested it might represent a projection effect, a structure that appears larger than it is because galaxies distributed across a range of depths along the line of sight happen to align in a way that inflates the apparent size. The debate was not fully resolved, but the Sloan Great Wall was close enough to the theoretical ceiling that the community could accommodate it without breaking anything fundamental. The Hercules Corona Borealis Great Wall is not close to the ceiling. It is, at its current best estimate dimensions, approximately 8 to 10 times larger than the theoretical maximum. That factor of 8 to 10 is not a rounding error. It is not an artifact of imprecise instrumentation. It represents a genuine crisis of explanation, a gap between what the standard model of cosmology predicts and what observations appear to show, wide enough to drive multiple competing hypotheses through it simultaneously. The first and most conservative hypothesis: the structure is a statistical artifact. The sky distribution of detected gamma-ray bursts is not uniform. Swift and its predecessors observed preferentially in certain directions, accumulated data unevenly over time, and the sample size of gamma-ray bursts with precisely measured redshifts, though growing, remains far smaller than galaxy redshift surveys used to map other large-scale structures. If the sample is sparse and anisotropically distributed, clustering can appear where none physically exists. This is not a fringe concern. It is the first thing any rigorous statistician would flag. The second hypothesis: the structure exists, but is not gravitationally coherent. Under this interpretation, the gamma-ray burst overdensity traces a real geometric feature in the distribution of matter, a vast, elongated sheet or filament, but the material within it is not gravitationally bound. It is simply matter that happens to share a similar cosmic address, spread across a region that looks connected from our line of sight, but is physically distinct. Gravitational coherence is the critical test. A structure that is merely geometrically large but dynamically disconnected does not violate the cosmological principle in the same way. The third hypothesis, and the one that keeps theorists awake, is that the structure is exactly what it appears to be: a real, physically coherent overdensity of matter at a scale that the lambda CDM model cannot produce. If that is true, then either the model is incomplete, the initial conditions of the universe were different from what the cosmic microwave background implies, or there is physics operating on gigaparsec scales that has not yet been incorporated into the standard framework. In April 2025, Horvath's team published a new analysis incorporating additional gamma-ray burst data gathered over the intervening decade. Their revised measurements suggested the structure is not only real, but larger than the original estimate, extending over a greater radial range, meaning its depth along the line of sight is also anomalous, and including gamma-ray burst sources at closer distances that were not previously recognized as part of the same structure. The Hercules Corona Borealis Great Wall, in their updated assessment, may be even more challenging to explain than the 2013 paper suggested. What drives the challenge deeper is the question the updated data forces. If the structure extends closer to us than originally thought, then we are not merely looking at a distant anomaly frozen in the early universe. We may be looking at something whose gravitational influence has persisted and perhaps grown across cosmic time. And that possibility changes the nature of the question entirely. The universe does not build its largest structures the way a mason lays bricks, deliberately, sequentially, with intention. It builds them the way a river carves a canyon, through the patient, indifferent accumulation of force over time, guided entirely by the geometry of what came before. To understand why the Hercules Corona Borealis Great Wall is physically problematic, you have to understand the machinery of cosmic structure formation from first principles, because the conflict is not in the observation alone. It is buried inside the mathematics of how gravity actually works across cosmological distances. Start with dark matter, not because it is exotic or mysterious, though it is both, but because without it, no large-scale structure exists at all. The ordinary matter that composes stars, gas clouds, planets, and every instrument humanity has ever built to observe the sky accounts for approximately 5% of the total energy content of the universe. Dark matter accounts for roughly 27%. It does not emit light, it does not absorb light. It has never been directly detected in a laboratory. Its existence is inferred entirely from its gravitational effects, the anomalous rotation curves of galaxies, the bending of light around galaxy clusters far beyond what visible mass can produce, and the specific pattern of temperature fluctuations in the cosmic microwave background, which encodes the acoustic oscillations of the early universe's matter radiation plasma with a precision that only makes sense if dark matter was present and structurally dominant from the very beginning. Dark matter forms halos, roughly spherical concentrations of mass held together by their own gravity. These halos collapse out of the primordial density fluctuations first, before ordinary baryonic matter can cool and condense into stars and galaxies. Ordinary matter falls into the gravitational potential wells that dark matter halos create, accumulating at their centers, where it eventually cools, fragments, and ignites into stellar populations. The galaxy you see in any telescope image is, in a real physical sense, the luminous tip of a far larger dark matter halo. The halo's mass typically exceeds the visible galaxy's mass by a factor of 10 to 100. The hierarchy of structure, the way the universe assembles itself from small to large, follows directly from the shape of the initial power spectrum of density fluctuations. This spectrum, measured to extraordinary precision by the Wilkinson Microwave Anisotropy Probe and the Planck satellite, describes how much clustering power exists at each spatial scale. Small scales, the scales of individual galaxies, have the most power, meaning the density fluctuations there are largest, and small structures collapse first. Larger scales have less initial power, meaning large structures form later, assembled from the merger and gravitational accretion of smaller ones. This is the hierarchical model of structure formation. It is one of the most rigorously tested predictions in all of cosmology. Galaxy-scale halos collapse within the first 100 million to 1 billion years. Groups of galaxies, collections of a few dozen to a few hundred members, form over several billion years. Rich galaxy clusters, containing hundreds to thousands of galaxies within regions a few tens of millions of light-years across, are still actively assembling today. Superclusters, the loosest, largest gravitationally influenced structures, form over the full age of the universe and are, in the current epoch of dark energy-dominated expansion, actually beginning to pull apart rather than continue assembling. Now apply those timescales to the Hercules Corona Borealis Great Wall. A structure 10 billion light-years across requires gravitational coherence at a scale of 10 billion light-years. For gravity to coordinate the behavior of matter across 10 billion light-years, a gravitational signal, traveling, like all signals in space-time, at a maximum speed of 300,000 kilometers per second, must be able to traverse that distance within the age of the universe. The universe is 13.8 billion years old. Light, traveling at maximum speed since the Big Bang, has covered approximately 46 billion light-years of co-moving distance due to the expansion of space. So a gravitational signal, in principle, could have crossed 10 billion light-years by now. The distance alone does not make the structure impossible. The impossibility comes from the growth rate. Gravity on cosmological scales is not only a function of distance, it is a function of the density contrast between a structure and the surrounding universe, the rate of cosmic expansion at the relevant epoch, and the presence of dark energy, which acts as a repulsive term in Einstein's field equations, suppressing the growth of structure on large scales. The mathematical tool that captures all of this is the linear growth factor, derived from perturbation theory applied to the Friedmann equations. It describes how much a given density perturbation can grow between an initial redshift and the present day. For the scales at which the Hercules Corona Borealis Great Wall operates, the linear growth factor, even integrated over the full age of the universe, predicts that density perturbations of the required amplitude simply cannot assemble into a coherent structure of that size within the available time. The numbers do not close. It is not that the assembly would be slow or difficult. It is that the physics of gravitational growth as encoded in the lambda CDM model produces a hard ceiling, and that ceiling sits roughly an order of magnitude below the observed structure. Think of it this way. If you dropped a stone into a pond, the ripple it creates expands outward at a specific speed determined by the water's surface tension and depth. You cannot produce a ripple 10 meters wide from a stone thrown 2 seconds ago if the ripple velocity is 1 meter per second. The physics sets the boundary, not the initial conditions. Cosmological structure formation operates under an equivalent constraint. The growth rate of density perturbations is bounded by the physics of the expanding universe, and that bound produces a maximum coherent structure size at any given epoch. Here is where the myth that most people carry about the universe's structure needs to be addressed directly. Many popular descriptions of cosmic structure use phrases like, "the universe is clumpy at all scales," or "structure extends all the way up." This is incorrect. The cosmological principle does not claim the universe is perfectly smooth at all scales. It claims the universe becomes statistically uniform above a characteristic scale. Below that scale, structure exists. Galaxies, clusters, superclusters, filaments. Above it, the distribution of matter should look homogeneous when averaged over sufficiently large volumes. This transition to homogeneity is not a philosophical assumption. It is a measured, observationally confirmed property of the large-scale galaxy distribution. The 2-degree field galaxy redshift survey, the Sloan Digital Sky Survey, and the VIMOS Public Extragalactic Redshift Survey all independently confirm that the galaxy distribution converges towards statistical homogeneity above scales of roughly 300 to 500 million light-years. The Hercules Corona Borealis Great Wall sits at 20 times that confirmed homogeneity scale. Not 2 times, not 5 times, 20. The tension deepens when you consider what the Planck satellite's measurements of the cosmic microwave background actually tell us about the initial density fluctuations. The primordial power spectrum, the blueprint of all structure in the universe, is well described by a nearly scale-invariant Harrison-Zeldovich spectrum with a spectral index of approximately 0.965. This means there was slightly more power on small scales than large scales in the early universe. The fluctuation amplitude at the scales corresponding to 10 billion light-years today was extraordinarily small at the time of recombination, far too small, under standard gravitational growth to have produced a density contrast large enough to define a coherent structure today. For the Hercules Corona Borealis Great Wall to be real and gravitationally coherent, the primordial fluctuation at its scale would need to have been anomalously large, a statistical outlier so extreme that its probability of occurring within the standard inflationary framework is vanishingly small. Inflation, the period of exponential expansion in the universe's first fraction of a second, does predict a nearly Gaussian distribution of primordial fluctuations. Extreme outliers are allowed in a Gaussian distribution, but their probability decreases sharply with amplitude. A fluctuation large enough to seed a 10 billion light-year coherent structure would sit so far out in the tail of the distribution that its occurrence in the single observable universe we have access to strains credibility under standard inflationary models. This is why the theoretical response to the Hercules Corona Borealis Great Wall has not converged on a single explanation. The options on the table range from extensions of inflation that produce non-Gaussian primordial fluctuations at large scales, to modifications of dark energy that allow faster growth of structure at high redshift, to topological defects, cosmic strings or domain walls left over from phase transitions in the early universe, whose gravitational influence could seed anomalously large overdensities. Each of these proposals is theoretically motivated. None of them is currently required by any other observational evidence, and all of them demand significant departures from the standard model. The most productive frame for the current state of the science is not, the model is wrong. It is, the model has a seam, and the Hercules Corona Borealis Great Wall is pulling at it. Every great revision in the history of cosmology began the same way. Not with a catastrophic failure of prediction, but with a single anomaly that refused to go away, a number that didn't close, a structure that shouldn't be there, a signal that arrived from the wrong direction. The perihelion precession of Mercury refused to go away for decades before general relativity explained it. The measured expansion rate of the universe refused to match theoretical predictions for years before dark energy was invoked to reconcile the data. The anomaly is not the end of the model. The anomaly is the door. What lies behind this particular door is something the next generation of instruments, the Vera C. Rubin Observatory, the Square Kilometer Array, the Nancy Grace Roman Space Telescope, will probe with a depth of data that makes today's gamma-ray burst surveys look like a handful of data points sketched on a napkin. The machinery is ready. The question is already written. In 2020, 7 years after the original paper detonated inside the cosmological community, Horvath's team returned. Not with a retraction, not with a quiet revision buried in a footnote. They returned with a new analysis, incorporating a larger and more carefully vetted catalog of gamma-ray bursts, applying more rigorous statistical controls for the observational biases their critics had identified, and using updated redshift measurements from improved ground-based spectroscopic follow-up. Their conclusion, published after scrutinizing the full weight of the accumulated critique, held. The Hercules Corona Borealis Great Wall, in their assessment, remained statistically significant. The structure was not an artifact of uneven sky coverage. It was not a projection effect inflated by lines of sight sampling. It was real, and it was large. That confirmation, arriving not in triumph but in the careful language of statistical significance thresholds and confidence intervals, was the moment the debate shifted its center of gravity. The scientific community had spent the intervening years doing what it does best, attacking the result from every angle simultaneously. Competing teams reanalyzed the original Swift data with different statistical tests. Some found the clustering less significant than Horvath reported, arguing that the team's chosen methods for measuring spatial randomness were not optimal for the sparse, anisotropically sampled nature of the gamma-ray burst catalog. The criticism was not unfounded. Gamma-ray burst catalogs are fundamentally different from galaxy redshift surveys. A galaxy survey can systematically tile the sky in a defined pattern, accumulating redshifts for every object above a flux threshold in a chosen area. Gamma-ray bursts arrive without warning, at random positions, at random times, detected by satellites whose pointing history is driven by entirely different observational priorities. The resulting catalog has gaps, uneven depth across the sky, and potential redshift incompleteness in ways that are difficult to fully characterize. Each of those limitations is a potential source of spurious clustering. When you sample a distribution unevenly, you can produce apparent overdensities simply from the geometry of the sampling, not from any real clustering in the underlying population. The critics who challenged the structure's reality were not dismissing the data. They were demanding that the statistical analysis account for the full complexity of how the data was acquired. What changed between 2013 and 2020 was not merely the size of the catalog, it was the quality of the redshift measurements. Photometric redshifts, estimates derived from the color of a source's light across a few broad filters, carry significant uncertainty. Spectroscopic redshifts, obtained by resolving the source's light into a detailed spectrum and identifying the precise wavelengths of known atomic emission or absorption lines, are accurate to a small fraction of a percent. The 2020 analysis leaned more heavily on spectroscopic measurements, tightening the redshift boundaries of the structure and reducing the probability that its apparent extent was inflated by measurement scatter. The structure narrowed slightly in some dimensions under the improved analysis, but it did not disappear. And its core statistical anomaly, the probability that the observed gamma-ray burst clustering in the Hercules Corona Borealis region could arise by chance in a truly homogeneous distribution, remained well below conventional thresholds for dismissal. Then, in April 2025, a new paper arrived. Using the most complete gamma-ray burst catalog assembled to that point, incorporating data not only from SWIFT, but from the Fermi Gamma Ray Space Telescope, which had been accumulating observations since its launch in 2008, and from ground-based follow-up programs spanning nearly 2 decades of international coordination. The team's updated analysis produced a result that compressed the air out of every room where cosmologists read it. The structure was not only confirmed, it was larger than originally reported. The revised extent, incorporating sources at closer distances that had not been attributed to the structure in 2013, pushed the Hercules Corona Borealis Great Wall's radial depth, its extent along the line of sight, as opposed to its extent across the sky, significantly beyond the original estimate. The three-dimensional volume occupied by the anomalous overdensity was substantially greater than a decade of previous analysis had suggested. And the closer boundary of the structure, now extending to redshifts below the original estimate, implied that the structure was not purely a feature of the distant early universe, frozen at a specific cosmic epoch. It had extent across cosmic time. That detail matters enormously. A structure frozen at a single redshift, a thin shell in cosmic distance, could conceivably arise from a rare geometric alignment, a chance superposition of unrelated overdensities along a particular line of sight. But a structure with significant radial depth, extending across a range of look-back times, is harder to dismiss as a projection artifact. It occupies real three-dimensional volume in a way that demands a physical explanation rather than a statistical one. The same 2025 analysis also addressed a hypothesis that had gained traction in the intervening years, that the Hercules Corona Borealis overdensity might be tracing not a single coherent structure, but a network of independent filaments and walls that happen to share a similar redshift range across a broad sky area. Under this interpretation, the structure would be more analogous to the full cosmic web at a particular cosmic epoch, a statistical overdensity in the large-scale matter distribution that is real but not gravitationally coherent in the way a single supercluster or filament is. This is a physically meaningful distinction. A gravitationally coherent structure is one whose components are causally connected, where the mass at one end has, over cosmic time, influenced the distribution of mass at the other end through gravity. A statistically overdense region is simply a place where the universe happened to put more matter, without those separated regions necessarily knowing about each other in any gravitational sense. The 2025 data could not definitively resolve that question. Resolving it requires velocity measurements, the peculiar velocities of galaxies within the structure, which reveal whether those galaxies are falling toward a common gravitational center or simply cohabiting a region of space without dynamic coordination. Gamma-ray burst host galaxies, identified at cosmological distances of 10 billion light-years, are not accessible to the spectroscopic surveys that measure peculiar velocities in nearby large-scale structures. The instrumentation required to do that work does not yet exist in its mature form. What the 2025 paper did establish was a more precise map of where the overdensity begins and ends, a sharper three-dimensional boundary for the anomaly. And that boundary, more clearly defined than at any previous point in the structure's observational history, sits in direct confrontation with the predictions of the lambda CDM model in a way that statistical uncertainty alone can no longer absorb. The confrontation crystallized around a specific number, the expected number of structures of this size and density in the observable universe, given the lambda CDM model's predictions for the primordial power spectrum and the subsequent growth of structure. That number is not zero. The lambda CDM model does not make perfectly sharp predictions. It generates probability distributions. But when you ask the model how likely it is to produce a single structure of the observed dimensions of the Hercules Corona Borealis Great Wall within the volume of the observable universe, the answer sits below any reasonable threshold for expected. The community's response to this accumulated weight of evidence has not been a paradigm shift announcement. Science does not work that way. What has happened, more quietly but more durably, is a reorientation of research programs. Teams that previously focused on galaxy redshift surveys at moderate distances began proposing gamma-ray burst follow-up programs at high redshift. Theoretical groups that work on modified gravity and non-standard dark energy models found a new empirical anchor for their calculations. The question of large-scale homogeneity, which had been treated as observationally settled for most of the 2000s, reopened with renewed urgency. And nested within that reopening is a deeper question that the data, taken at face value, forces onto the table. The cosmic microwave background is the universe's baby picture, the earliest snapshot of the matter distribution taken when the cosmos was 380,000 years old. The temperature fluctuations imprinted on that background are Gaussian, nearly scale invariant, and consistent across the sky to 1 part in 100,000. They are the seeds from which all subsequent structure grew. If those seeds evolved forward by 13.8 billion years of gravitational growth under the known physics of dark matter, dark energy, and general relativity, cannot produce the Hercules Corona Borealis Great Wall, then either the evolution was different from what the model describes, or the seeds themselves contained information that the cosmic microwave background does not reveal. Both possibilities are extraordinary. Either the growth of structure proceeded differently from what the most successful cosmological model in history predicts, which means the model is missing physics, or the initial conditions of the universe were not what the cosmic microwave background implies at the scales that matter for this structure, which means inflation produced something more complex than the standard single-field slow-roll scenario describes. ESA's Theseus satellite, proposed for launch in the early 2030s, would increase the gamma-ray burst redshift catalog by orders of magnitude with uniform sky coverage and systematic spectroscopic follow-up built into the mission architecture from the start. For the first time, the spatial statistics of gamma-ray bursts at cosmological distances would be measured with a completeness comparable to what the Sloan Digital Sky Survey achieved for galaxies at much closer distances. Theseus will not merely test whether the Hercules Corona Borealis Great Wall is real. It will map the full topology of the universe's large-scale matter distribution at the epoch where the anomaly lives, and produce the first catalog deep enough to tell whether the structure is one anomaly or one of many. That answer, when it comes, will not be quiet. The observable universe spans approximately 93 billion light-years in diameter. Within that sphere, the volume of space whose light has had time to reach us since the Big Bang, there are an estimated 2 trillion galaxies distributed across the cosmic web in filaments, sheets, and voids that trace the gravitational skeleton of dark matter assembled over 13.8 billion years of cosmic history. 2 trillion galaxies. And yet, carved into the fabric of that distribution, there is a region, a single region, whose dimensions exceed every other known structure in the observable universe by a factor that has no comfortable precedent. The Hercules Corona Borealis Great Wall does not sit at the edge of the observable universe, in some remote region inaccessible to scrutiny. It sits at a redshift of approximately 2, in a sky direction visible from both hemispheres, spanning the constellation boundaries of Hercules and Corona Borealis, 2 well-studied regions of the northern sky that have been mapped, surveyed, and catalogued for decades. It is not hidden. It is not ambiguous in its sky position. What is ambiguous? What remains the central, unresolved question in the entire body of literature surrounding it is whether the overdensity of gamma-ray bursts that defines it corresponds to a single gravitationally coherent physical structure, or to something more complex, more distributed, and potentially more challenging to explain. Both possibilities are extraordinary. Neither is comfortable. At the scales where this structure lives, the universe is doing something that the Standard Model's most sophisticated simulations do not predict. The illustrious TNG simulation, one of the most computationally advanced models of cosmic structure formation ever run, incorporating dark matter dynamics, gas physics, stellar evolution, black hole feedback, and magnetic fields across a comoving volume of 300 megaparsecs per side, reproduces the observed properties of galaxies, clusters, and large-scale filaments with remarkable fidelity across a wide range of scales. It does not produce a Hercules Corona Borealis Great Wall. Neither does the Millennium simulation, which mapped the evolution of more than 10 billion particles of dark matter through 13 billion years of simulated cosmic time. Neither does any lambda CDM simulation run to date, at any resolution, using any variation of the standard cosmological parameters. The structure, at its observed dimensions, falls outside the phase space that these simulations can access. That statement requires precision. It does not mean the simulations are wrong about everything they model. They are not. The lambda CDM model remains the most successful framework in the history of cosmology, correctly predicting the cosmic microwave background power spectrum, the abundances of light elements produced in Big Bang nucleosynthesis, the clustering of galaxies on intermediate scales, the accelerated expansion of the universe confirmed by Type Ia supernova surveys, and the distribution of galaxy clusters across cosmic time. This is not a broken model. It is a model with a seam. And the Hercules Corona Borealis Great Wall is pulling at that seam from a direction the model's architects did not anticipate. What the seam reveals, when you trace it carefully, is a tension between two independently measured quantities: the amplitude of density fluctuations on large scales and the predicted growth rate of those fluctuations under lambda CDM. The parameter cosmologists use to quantify this is called sigma 8, the root mean square amplitude of matter density fluctuations averaged over spheres of 8 megaparsecs in radius. Its value is determined both from the cosmic microwave background temperature fluctuations extrapolated forward to the present day using the lambda CDM growth equations, and from direct measurements of large-scale structure, including galaxy clustering surveys and weak gravitational lensing observations. For over a decade, these two independent measurements of sigma 8 have disagreed with each other at a level of statistical significance that the community calls a tension. Not a contradiction, not a proof of new physics, but a persistent, reproducible discrepancy that has survived improvements in both measurement techniques and theoretical modeling. The cosmic microwave background implies slightly more clustering power than is observed in the late universe. Matter is slightly smoother at large scales than the early universe's imprint predicts it should be under standard gravitational growth. This is the sigma 8 tension. And the Hercules Corona Borealis Great Wall sits at the extreme end of the same discrepancy, a structure so anomalously large that it represents not a mild statistical disagreement, but a categorical outlier in the distribution of structure sizes the lambda CDM model generates. The physical picture of what this structure actually is, if it is real and coherent, demands reverence for scale that ordinary language struggles to convey. At 10 billion light-years in its longest dimension, the Hercules Corona Borealis Great Wall spans approximately 11% of the diameter of the entire observable universe. If you were somehow positioned at one end of the structure and attempted to send a light signal to the other end, that signal, traveling at 300,000 kilometers per second without interruption, would take 10 billion years to arrive. The universe would be more than twice its current age before your message reached the other side. The structure is not merely large relative to human experience. It is large relative to the universe itself. Every known galaxy cluster sits inside a region of space that a signal traversing the full length of the Hercules Corona Borealis Great Wall would pass through and leave behind in the time it takes our Sun to complete roughly 40 orbits of the Milky Way's center. The Sun's orbital period around the galactic center is approximately 225 million years. 40 of those orbits span 9 billion years, less than the signal's travel time across the structure. The structure was identified through gamma-ray bursts. It is worth dwelling for a moment on what it means for the universe's most violent events to serve as the tracers of its most extreme architecture. A gamma-ray burst produced by the core collapse of a massive star releases in a matter of seconds more energy than our sun will emit across its entire 10 billion-year lifespan. These are not subtle signals. They are the universe operating at peak intensity. Stellar cores collapsing under their own gravity into neutron stars or black holes, launching jets of relativistic plasma at greater than 99% the speed of light, producing flashes of gamma radiation detectable across the full observable universe. That such events, the deaths of the most massive stars, the mergers of the densest stellar remnants, trace an overdensity of matter at 10 billion light-years is not an accident. Star formation follows matter. Where matter clusters, stars form. Where the most massive stars form, they die violently and quickly, their lifetimes measured in millions of years, not billions. The gamma-ray burst rate at any cosmic location is a proxy for the massive star formation rate, which is itself a proxy for the underlying matter density. The overdensity of gamma-ray bursts in the Hercules Corona Borealis region is, in this chain of inference, an overdensity of massive star formation, which traces an overdensity of matter. The chain is not perfectly calibrated. There are known environmental and metallicity effects that modulate gamma-ray burst production rates, but the statistical excess is robust enough to have survived over a decade of independent scrutiny. The 2025 reanalysis extended the structure's confirmed redshift range to span from approximately 0.33 to 2.43, meaning the overdensity is not confined to a thin shell at redshift 2. It has depth in cosmic time. It begins at a look-back time of roughly 3.8 billion years and extends to a look-back time of over 11 billion years. The universe, when the near boundary of this structure emitted the gamma-ray bursts we now detect, was already 8 billion years old, well past the peak of cosmic star formation, which occurred around redshift 2 to 3. The universe, when the far boundary emitted its bursts, was less than 3 billion years old, deep in the epoch of maximum stellar activity. A structure with coherent existence across that range of cosmic epochs is not a snapshot of the early universe. It is a persistent feature, something that was already anomalously large when the universe was young, and that persisted through 8 billion more years of cosmic evolution. The specific architecture of its persistence is unknown. Whether the galaxies within it share a common infall velocity toward a gravitational center, whether the dark matter distribution within its boundaries is a single connected overdense region or a collection of individual halos that happen to share a sky direction, whether its boundaries are sharp or gradual, none of this has been measured. The instruments required to measure it do not yet exist in their operational form. The Theseus satellite, proposed by the European Space Agency as a mission dedicated specifically to gamma-ray burst science and cosmology, would provide the spectroscopic completeness and sky coverage uniformity required to answer these questions definitively. Its launch, if approved in its current planning timeline, falls in the early 2030s. The wait is not passive. Every year, the Swift catalog grows. Every year, Fermi accumulates more bursts with measured redshifts. Every year, ground-based follow-up programs add spectroscopic confirmations to sources that previously carried only photometric redshift estimates. The dataset that will ultimately resolve the question of the Hercules Corona Borealis Great Wall's physical reality is being assembled, observation by observation, across the networks of a global astronomical community working in near real time. The universe, it turns out, does not reveal its largest secrets quickly. It releases them one photon at a time, across billions of years of travel, into instruments built by a species that has existed for less than 300,000 years on a planet orbiting an unremarkable star in the outer arm of a galaxy that is, itself, a vanishingly small component of the structure we are trying to understand. That asymmetry, between the scale of the question and the scale of the questioner, is not a reason for despair. It is the precise condition that makes the science extraordinary. The structure is there. The seam in the model is visible, and the instruments are being built. John Hakila of the University of Alabama in Huntsville, one of the three astronomers whose work first brought the Hercules Corona Borealis Great Wall into the scientific literature, said it plainly after the 2025 reanalysis. It probably extends farther than the 10 billion light-years we had previously identified. It is larger than the size of most anything to which it might be compared. That sentence, delivered in the measured language of a working scientist, carries more weight than it appears to carry. It is not a claim about a distant abstraction. It is a statement about the physical architecture of the universe we inhabit. A universe whose geometry, at its largest accessible scales, contains something that the best theoretical framework humanity has ever assembled cannot fully account for. The true extent of the structure, Hakila added, remains undetermined. The gamma-ray burst sample is not yet large enough to place a firm upper boundary on its size. It may be larger still. The boundary the 2025 analysis established, a redshift range from 0.33 to 2.43, is a boundary defined by data availability, not by the structure's actual edge. Where the Hercules Corona Borealis Great Wall ends is, at this moment in the history of astronomy, genuinely unknown. That condition, a structure whose full extent we cannot yet measure, is not a failure of science. It is a precise description of where the frontier of observational cosmology currently sits. The frontier is not at the edge of the observable universe, where the light reaching us has been traveling for 13.8 billion years and carries only the faintest, most redshifted signals our instruments can detect. The frontier is right here, in the middle distance of cosmic history, at a redshift of 2, in a patch of northern sky that amateur astronomers can locate with a star chart. The largest known structure in the observable universe is not hiding. It is simply larger than our current tools can fully measure. The history of observational astronomy is, in one reading, a continuous record of discovering that the universe is larger, older, and more structurally complex than the previous generation of instruments could resolve. William Herschel, mapping the distribution of stars visible through his telescopes in the 18th century, constructed a model of the Milky Way that placed the sun near its center. Not from arrogance, but from the genuine limits of his photometric data, which could not penetrate the dust lanes that obscure the galactic plane. The galaxy was larger than he could see. Henrietta Swan Leavitt, measuring the periods of Cepheid variable stars in the Magellanic Clouds in the early 20th century, established the first reliable method for measuring cosmic distances beyond the reach of parallax, and in doing so, handed Edwin Hubble the tool that proved the spiral nebulae were independent galaxies, not local structures within the Milky Way. The universe was larger than the previous consensus had allowed. Each expansion of the known universe followed the same pattern. A measurement technique reaches its natural limit, a new technique or instrument extends the reach, and the cosmos reveals a layer of structure that the previous limit had concealed. The transition from optical galaxy surveys to gamma-ray burst mapping as a probe of ultra-large-scale structure is the current iteration of that same historical pattern. And the Theseus satellite, the proposed ESA mission designed to detect, localize, and spectroscopically characterize gamma-ray bursts across the full observable universe with uniform sky coverage, represents the next extension of reach. What Theseus would provide beyond raw numbers is completeness. The existing gamma-ray burst catalogs are accumulated from opportunistic observations. Satellites built primarily for other scientific goals, pointing at different parts of the sky for different durations, with ground-based follow-up dependent on weather, telescope scheduling, and the alert response time of individual observatories. The resulting catalog is a brilliant but irregular mosaic. Theseus would replace that mosaic with a systematic survey, a uniform sampling of the gamma-ray burst population across the full sky and the full accessible redshift range. For the first time, the spatial statistics of matter distribution at cosmological distances could be measured with the same rigor that galaxy surveys achieved at intermediate distances in the 1990s and 2000s. The science that would follow is not merely confirmatory. A Theseus-class catalog would be sufficient to test whether the Hercules Corona Borealis Great Wall is an isolated anomaly or the first detected member of a population of ultra-large structures distributed across the observable universe. If it is isolated, the probability calculus shifts modestly in the lambda CDM model's favor. A single extreme outlier in a Gaussian distribution of structure sizes is statistically painful, but not fatal. If the catalog reveals multiple structures of comparable scale, the cosmological principle faces a challenge that statistical uncertainty alone cannot absorb. The sigma-8 tension, meanwhile, has not resolved. The most recent analyses from weak gravitational lensing surveys, including the Kilo-degree survey and early data from the Euclid Space Telescope, continue to find a matter clustering amplitude slightly below the value the cosmic microwave background predicts under lambda CDM. A 2026 analysis published in Nature Astronomy suggested that interactions between dark matter and neutrinos could suppress structure growth at late cosmic times in a way that reconciles the early and late universe measurements of sigma-8. The proposal is mathematically consistent and physically motivated. It is not yet confirmed by independent data. It joins a list of candidate solutions: modified gravity, interacting dark energy, non-standard neutrino physics, each of which resolves the sigma-8 tension at the cost of introducing new physics that must itself be tested against the full body of cosmological observations. Science does not choose between these candidates by preference, it chooses by evidence. And the evidence, accumulating observation by observation across the global network of telescopes and satellites and computational facilities that constitute modern astronomy, has not yet converged on a single answer. That is an honest statement of the situation. Not a confession of ignorance, but an accurate map of where the boundaries of confirmed knowledge currently lie, and where the territory beyond those boundaries begins. The Laniakea supercluster, the large-scale structure within which the Milky Way resides, spans approximately 500 million light-years and contains the mass of roughly 100 million billion suns, distributed across more than 100,000 galaxies. It is the largest gravitationally defined structure whose membership and dynamics have been quantitatively mapped using peculiar velocity surveys. The Hercules Corona Borealis Great Wall dwarfs it by a factor of at least 20 in linear dimension. The two structures are not comparable in kind. Laniakea is a measured, dynamically characterized gravitational basin. The Hercules Corona Borealis Great Wall is an overdensity whose three-dimensional dynamics remain unmeasured, whose gravitational coherence remains unconfirmed, and whose full extent remains unknown. And yet the evidence for its existence has not weakened with time. It has strengthened. Every independent reanalysis that set out to demonstrate the structure was a statistical artifact returned, instead, with a refined and more constrained picture of its reality. The 2020 reanalysis confirmed the clustering against improved statistical controls. The 2025 reanalysis confirmed it again, extended its boundaries, and demonstrated that the extension was not attributable to sampling biases. The trajectory of the evidence across more than a decade of independent scrutiny has moved consistently in one direction. The universe contains something at 10 to 15 billion light-years in scale that should not exist under the physics of the standard cosmological model. The model that cannot produce it is otherwise the most successful quantitative framework in the history of science. Both of those statements are simultaneously true. The tension between them is not a paradox requiring resolution by choosing one over the other. It is a productive scientific problem, the kind of problem that, when solved, expands what we know about the nature of space, time, matter, and the initial conditions from which everything we can observe emerged. The largest thing in the observable universe is pulling at the seams of the largest theoretical framework humanity has ever built. The seam has not torn, but it is not silent. Every photon of gamma radiation that crosses 10 billion light-years of expanding space and arrives at a detector on a satellite in low Earth orbit is a single data point in the ongoing measurement of that tension. Billions of years in transit, fractions of a second of detection. The data accumulates, the picture sharpens, and the question, whether the universe is, at its deepest accessible scale, what we think it is, remains precisely, rigorously, beautifully open.